Hello, and welcome to the first handout for the calculus supplement for the second semester of college physics. So these handouts are going to be all about electricity and magnetism and other modern physics topics like relativity and quantum mechanics. And we're going to start with Gauss's law, the topic of today's lecture. All right, our objective in part one about Gauss's law is to understand that Gauss's law is represented by a surface integral of the electric field that is parallel to the normal of the surface. Now, these lectures only make sense if you've already seen the ideas presented in the lectures on electricity and magnetism, okay? Okay, so let me talk about the electric field among other things. Now, one thing I want to do sometimes in these lectures is talk about key calculus concepts if it's necessary. And in this case, one of those key concepts certainly is necessary to discuss, and that's the surface integral. What is a surface integral and how is it different from other types of integrals? Okay, well, it is an integral that integrates a scalar value over the entirety of a defined surface. So just like an integral looks across a function and calculates the output of that function at tiny, tiny intervals into infinitesimally small intervals, we're doing the same thing, but in two dimensions over a grid of values, so to speak. The process of solving a surface integral requires splitting an area into infinitesimally small areas. All right, so imagine one big area like a sheet and then tiny little segments of that sheet. And I'll show you a sketch in just a minute. And we will call those area elements, just like we would split a axis into little tiny elements called dx, right? That's just an infinitesimally small length of x. Same idea here, but it's an area. All right, so this is the area element. And determining a scalar value at each one of those elements, because each one of those elements has some output, because it's the function output of this surface. Okay, so really what we're talking about here is multivariable functions, because a function, for example, of x and y can be defined as a surface. Okay, it's like giving you the height at different coordinates of x and y. Okay, all right, so let's move down to our key formulas, because we're going to put this surface integral, zoom out a bit there, to the test with a physics concept, okay, involving magnetism. All right, actually at this point, electricity only, okay, just the flux. All right, so let's take a look at it. So here is Gauss's law in integral form, okay? Gauss's law can be represented algebraically as well, but here it is in integral form, okay? This right here is uppercase phi, that's the letter. The subscript denotes electric, and it is the electric flux. Because uppercase phi we use for flux, we talk about magnetic flux as well, which is why a moment ago I said magnetic, okay? The units of electric flux are volts per meter times area, because of course the electric field is volts per meter. That's one way to express it. And you're multiplying by area, so it becomes, well, once you cancel out one of the meters, it becomes voltmeters. So electric flux is potential times distance, okay? All right, and it's equal to this integral. Well, that's the surface integral, all right? And that surface integral is then going to be equal to itself the charge within the surface, okay? Divided by a constant of the universe, the permittivity constant. And the permittivity constant is equal to 8.85 times 10 to the negative 12 farads per amp. Okay, so when we look at the surface integral, inside of it we see some vectors and we see a dot between them. Well, that denotes a dot product, all right? And it's a dot product of the electric field vector and the normal vector of that surface element, okay? So that's hard to visualize, but I have a sketch that I think will help. So this is some entire surface, okay? This is what we'd be integrating over, all right? That's the purpose of the integral, right? Lots and lots of tiny summations. The area element is dA, okay? It's this little pink rectangle here, right, on this curved surface. The dA vector is a vector that's normal to the surface, so just exactly perpendicular to this surface, okay? And remember, the surface itself is infinitesimally small. I just drew it as a rectangle, okay? Then we have the electric field, okay? Well, the electric field is coming out of the surface, right? So it's essentially piercing the surface. Here's the electric field vector. And there's some angle between that normal vector and the electric field vector, okay? And that's what we get when we do the dot product, okay? The dot product gives us the component of the electric field that's parallel to the normal vector of the area element. That's the purpose of a dot product. And the result of the dot product is, of course, a scalar, right? It's just a value, okay? It's just the value of the output at this particular point, okay? The scalar value at dA. That's the output of the dot product, okay? So that's one individual case, okay? That's what's going on inside of the integral. And then we're going to be doing that over and over again an infinite number of times on every little area element as we cover the entire surface. Okay, that's what a computer might do in practice, right? It might actually go over and just do each one manually, right? Finding the angle, because we could have an electric field that varies in angle as we go over the surface, varies in strength and angle. Both of those are completely solvable with this full definition. Now, even with calculus, however, we still aren't going to have those fully complicated cases, because if the angle is changing so that this dot product is changing as a function of the angle as well as a function of the magnitude of the electric field, it'd be a very difficult integral to actually solve in practice. So we're actually only going to deal with cases in this lecture where the electric field is exactly parallel to the normal vector. Okay, so we're actually not really going to use this dot product. Instead, we're going to deal with the charge enclosed, and you'll see what I mean. Okay. So quick note about the dot product. When you take a dot product, it's the same as just looking at the parallel components, as I just said. And so then in terms of the actual function, it's cosine of theta, theta being the angle between the two vectors. And do note that if the angle is 90 degrees, then there's no flux. And if there's no flux, then we're going to have no enclosed charge, okay? Because if there's no flux, that means all the electric field is either just skimming the surface of, just skimming along rather than piercing the surface, or there's just as much coming in as coming out of a closed surface. Now, speaking of closed surfaces, that's what we're going to be looking at with both the examples. All right, so let's do two examples that use Gauss's law, use in calculus, but aren't really going to be dealing with the surface integral, but instead integrating over the enclosed charge, okay? All right, so we have an electric charge Q that is distributed uniformly throughout a non-conducting sphere, okay? There's our non-conducting sphere right here. It has a radius R naught. You can kind of see it squeezed in there between all the plus signs. Plus signs just denoting the spread of positive charge, okay? And we want to determine the electric field outside the sphere, right? So that's for some value of R that is larger than R naught, and inside the sphere for some value of R that is smaller than R naught, okay? Now, little r without the subscript is a variable. It's what we're interested in, okay? Okay, so one thing is that the distribution is uniform and that it's non-conducting. Quick concept there, that's because if this was a conductor, all the charge would be on the surface because like charges repel, and the way that they can distribute themselves furthest apart is to be all on the surface. It's only in things like insulators where you can actually have charge that's evenly distributed throughout the entire volume, okay? All right, well, let's take a look at how we would do this, okay? So here's the electric field, right? So after all, we are using Gauss's law. This dotted line would be an example of a Gaussian surface, right? That's the whole point of Gauss's law and the surface integral, okay? And notice the electric field, no matter where it points, is always going to be perpendicular to the surface and all the little area elements of that surface. So that means that the surface integral is just going to give us E times A, okay? All right, so here we have our surface integral, all right? And then because every one of them is perpendicular, I can simplify the dot product to just plain old multiplication, okay? The surface that I'm going to be integrating over is a spherical surface, okay? That means that the area is just the surface area of a sphere. It's just 4 pi r squared. So it means my integral just becomes E 4 pi r squared, okay? So I told you, this part is trivial in a sense, right? We're not doing much with it. We're just going to be going to E times the surface area, okay? Now, we're going to be setting that equal to the enclosed charge, okay? Because by definition, that's what Gauss's law tells us. The electric field that's coming out must be equal to the enclosed charge, because otherwise, where would the electric field go, right? There's charge in here. That means we can trace that charge by how much electric field emanates from it, because our Gaussian surface is a complete closed surface. It's a spherical shell, okay? All right. And that means that when we solve for the electric field, we get this result right here. Now, this should look really familiar because this is just the electric field for a point charge. Because in part A, when we were looking outside the sphere, this even distribution of charge might as well have been a point charge. Because once we're outside of it, it acts like a point charge, okay? And that's a very fascinating result. It doesn't matter if it really is a point charge or not, we still get the electric field, which is a function of distance. As we get further away, it decreases with the square of distance, okay? The electric field strength does. All right, so what about within the sphere, okay? Well, let's think about that. We'll go back to Gauss's law. get the same result, okay? Now, what's going to happen in this case is this r squared is less than r naught. So how does that affect things? Well, it affects things because now this q enclosed isn't equal to the total charge q. Because notice last time I just sort of nonchalantly set the surface integral equal to the enclosed charge and just said it was q. It was the total charge. But if we have some smaller area like this one here, well, it's not the total charge anymore. It's just how much is enclosed inside of that smaller volume. Okay. So that means our enclosed charge is equal to a ratio of volume and distribution of charge, okay, divided by volume and distribution of charge for the whole sphere, okay? So this is a ratio, okay? Because the idea here is that this is just the volume and the distribution of charge, okay? This is a density. This rho sub E is a density of charge. Density of charge. Okay, and this makes perfect sense because as we get a smaller and smaller volume, we get a smaller amount, okay? Okay, the charge density is coulombs per cubic meter. That's what the rho represents here. It's not like mass density. Rho typically represents kilograms per cubic meter, but here it's charge per cubic meter because that's what we care about here. That's what we're talking about. Okay, well, the volume is just the volume of a sphere. Just like here, I use the surface area of a sphere and says 4 pi r squared, right? Common formula. The volume of a sphere, excuse me, is 4/3 pi r cubed, okay? And here's the thing. The density, or the distribution, the density, is the same in the smaller section as it is in the bigger section because it's uniform, okay? So that means this rho term here just cancels out, right? As does here the volume for the entire sphere. So look at the only thing that doesn't cancel, the variable r and the overall r naught, okay? Because this is some smaller r, and this is the overall value, the actual permanent radius. In other words, r naught is a constant, r is a variable, okay? And then we still have q, okay? Which is the total charge, just like this is some proportion of that total charge. Therefore, the proportion of the total charge is enclosed by some spherical Gaussian area that's smaller than the actual size of the sphere is r cubed over r naught cubed times the total charge. Interesting. So now we'll go ahead and replace that q enclosed with this expression, okay? The permittivity constant is along for the ride. And now we can simply solve for the expression for the electric field, and there we go, all right? So notice my expression for the electric field. It now has a r naught cubed in the denominator, whereas before it was just a variable r squared in the denominator. And now the variable is actually on the top. It's in the numerator, okay? So that means the electric field is growing as we go from r equals 0 up to r equals r naught. But that makes sense, of course it is, because if I'm at the very center and my Gaussian surface is infinitesimally small, it doesn't enclose really any volume, then there's no electric field yet, because I haven't enclosed any charge. As I get bigger and bigger surfaces, I'm enclosing more charge, thus my electric field is strengthening, okay? And it's actually strengthening linearly. We can show with the calculus that the relationship is linear growth. If we were to graph this as electric field strength going from r equals 0, passing through r equals r naught, and then just going on as r becomes bigger than r naught, we initially have linear growth electric field, and then the familiar 1 over r squared, decrease, okay? All right, and that's just electric field as a function of distance from the center of the sphere. All right, good. So again, see what we're doing here. We're more interested in really kind of applying Gauss's law and thinking about the charge distribution than we are the surface integral, other than conceptually having the surface integral make sense of the electric field piercing our surface. Now, what we're going to do in the second example, the second and last example for this section, is look at a non-uniform. Get rid of the uniform part. Have a charge distribution that varies as a function of the radius. So let's see what that looks like. Okay, so example 2. Suppose the charge density of the solid sphere in the figure shown is given by this density function, all right? Alpha times r squared. Alpha is just a constant, okay? And we can find that constant. So we're going to find alpha in terms of the total charge, because we know there's some total charge Q, again, on a sphere, right? Again, it's a non-conducting sphere of some sort. But here, as r gets bigger, there's more charges. Because notice what's happening here, right? The density means that as you get closer to the surface, there's more charges. And this is actually a very realistic density distribution, right? Because again, it's growing with R. Because what's going to happen if this is maybe like a semiconductor is the charges are still going to be somewhat free to move. So some of them are going to be able to move and cluster on the surface where they're going to be further apart. Other ones that are trapped are going to get left behind. And that's going to make this density function, like again, gets denser as we get closer to the surface of the sphere. Okay? And there's still total charge Q, as I just said. All right, so let's find that variable alpha. And the reason, again, is because in part B, then we're going to find the electric field, the thing we really care about. So finding alpha is just a step there, okay? Again, it's just a constant that doesn't actually allow us to have a numerical solution. Okay? So the total charge integral, right, is Q equals the distribution times the volume. Now, where is this integral coming from? Well, it's just kind of coming from the basic idea of a volumetric integral, not a surface integral, just summing up over volume elements, okay? Because this dV is a volume element, just like dA was an area element, and it would be equal to the surface area of a spherical shell times the infinitesimal thickness of that shell. Because that's what we're doing here. We're nesting an infinite number of tiny, tiny shells in order to actually integrate the value, right? So these each are these shell volume elements, okay? So dV is going to be replaced by 4 pi r squared dr, okay? And then we're going to replace just this generic density function with its actual form for this problem, alpha r squared, all right? And we're going to be integrating from the center of the sphere up to its surface, okay? Because here we don't care about outside of its surface, because actually outside we could show is just going to be act like a point charge again as soon as we leave the surface, okay? But within the surface, we're going to have an interesting result in terms of what the volume looks like, or what the electric field looks like, okay? All right, so moving on, we'll pull the constants out of the integral and combine our two r squared terms to get r to the fourth. Then we'll go ahead and solve that integral, and there we go. We have a value for total charge is equal to this, okay? And this is weird, right? Because total charge, why is it equal to, meters to the 5th power? That doesn't make sense. It should be, should be coulombs. Well, that's because alpha's here, and alpha has the correct dimensions to make this work. That's the whole point of why it was in that function, is just a general variable. But now we can solve for alpha. All I do is just cross multiply, and I've got that alpha is equal to 5 times the total charge divided by 4 pi times the radius to the 5th power, okay? So the units would be coulombs meters to the 5th, right? Odd units, but it works, okay? And it actually also makes sense because remember density, after all, was coulombs meters to the 3rd. So you can think about if you have a meter second over here and you divide both sides by meters, to the 2nd power, then you can get meters to the 5th, okay, in the denominator. But now we're set up to go to part B, find the electric field as a function of R inside that sphere, okay? Okay, so how do we do that? Zoom out a tad here. Well, we go to this again, the definition of the enclosed charge, okay? We'll get back to Gauss's law in just a minute, but Gauss's law is really just the last step, okay? Now we're going to set this up, okay? It's the same first step, isn't it, right? Now what's gonna be different here is we're gonna plug in for alpha, okay? So instead of just solving the integral in order to find alpha, now we know what it is, so we can actually place it in here. Furthermore, notice that we're no longer integrating. There is actually one important difference. We're no longer integrating from 0 to r naught, because we're not going from the center all the way to the outside, but instead we're integrating from 0 to the variable r, because we're trying to find the function form of it, okay, rather than just a value. All right, hopefully that makes sense. Okay, now notice we did the same thing with dV, right? I guess we already did that here. We replaced dV with the surface area times the thickness of our shell that we're integrating over. And now we can go ahead and cancel out some terms that are both in the numerator and the denominator and combine our r squareds, okay? And then solve the integral, because I have r squared, that's gonna give me another r to the 5th. When I actually do the integral following the rules of polynomials for antiderivatives, my 5s will cancel because I'll have a 5 up top and a 5 in the denominator. And then I'm gonna have a r naught squared and an r to the 5th, right? Or r naught to the 5th, so you see in squared, but r naught to the 5th and the variable r to the 5th. Okay, so that means that my enclosed charge is equal to this. Oh, that's interesting, because that's telling me that my enclosed charge doesn't grow linearly anymore, right? It grows with this complicated relationship between the radius, the variable, and the fixed width of the non-uniform distribution, non-conducting sphere, okay? So now finally, we'll take this back to Gauss's law, all right? And we know that the electric field times the surface area is gonna be equal to the enclosed charge over permittivity. We're gonna replace enclosed charge with this relationship here. all right? And then it's just a matter of solving for the electric field, and there we go, all right? So this is really interesting because this tells us that inside of this sphere, rather than it growing linearly, it's growing to the third power. So we actually have real steep growth of the electric field inside the sphere right up to the surface, okay? Getting steeper and steeper, right? Because it's a steep r to the cube function here. And then suddenly reaching a point where it starts falling off because now it's stacking like a point charge once we leave. And again, here I'm just extrapolating the idea that it has to behave like a point charge once we're outside of this non-conducting sphere, okay? But unlike in the last one when it was uniform and we had a linear function here, now it's r to the cubed. All solved from doing our integrals of charge distribution, okay? And they're all spherical, all right? All right, very good. Well, that is our first topic. Let's go on to our second related topic, all about voltage and electric field. All right, so this is the electrical potential gradient, okay? So what is the electrical potential gradient? Why would we talk about it at the same time as talking about Gauss's law? Well, we want to understand that the definition of the electrical potential difference is the line integral of the field parallel to a defined path. Oh, we're talking about a different kind of integral here. Now we're talking about line integrals, okay? We want to understand that the definition of electrical potential can be split into components to form the electrical potential gradient. Okay, so the transition here is because, after all, Gauss's law really defines the electric field, the idea of it representing enclosed charge and being tied to whatever enclosed charge there is. Well, how do then we think about voltage? Because voltage is the next abstraction from electric field, because voltage is all about changes in potential energy, and the electric field represents the force that does the work that creates that change in potential energy. Okay, so let's see then, how do we approach this with calculus? How do we relate the ideas of voltage and electric field? So let's cover 3 quick key calculus concepts: the line integral, the gradient, and the partial derivative. Okay, so the line integral is an integral of scalar values along a defined path. Okay, in practice, this involves integrating the value on path elements dl. So just like we've seen area elements and volume elements, these infinitesimally small things, now we just have dl. Now the only difference here is this isn't dx or dy, this is L, which L is a curve, not a straight line, see? Okay, so it's more like a curve integral than a line integral. What is a gradient, okay? Well, a gradient is a vector of partial derivatives of a vector field function, okay? Now, what's a vector field function? Well, that's what the electric field is. The electric field is a vector field function. If I have the electric field as a function of x, y, and z, that's just the direction of the vector at coordinates of x, y, and z, okay? And in practice, the vector field function takes the form of that function of 3 variables, okay? All right, now I mentioned partial derivatives. What is a partial derivative? Well, it is denoted by this symbol, which doesn't actually have its name. It's just the partial derivative symbol. It's a curly d, okay? And the derivative of a function, it is the derivative of a function of multiple variables, like this one here, with respect to only one of those variables, okay? So for example, if I have a function of x, y, and z, that's 2x squared times y plus 3xz squared, well, then I take a partial derivative of that function just with respect to x, shown here, then the y is a constant, and so is the z. So that means the only thing I actually have to take the derivative of is the x. So then my 2x squared y term becomes 4xy, and then this just becomes a constant, right? It just becomes 3z squared. Okay, that's the idea of a partial derivative. We'll be doing that in the one example. All right, well, what about the physics terms? Well, the good idea here is an equal potential surface. Now, with voltage, if you recall, voltage is called electrical potential. Those are synonyms, okay? We're probably more used to calling it voltage, but its technical term is electrical potential, all right? Well, you can have a equal potential line, which is just a line where all the voltage values are the same. Well, in 3 dimensions, you can have a surface where all the voltage values are the same. Okay, so let's go over here. So it's a surface of equal electrical potential, which is to say equal voltage, okay? It'd be like having a flat plane in terms of, like on the ground, that's all the same elevation. If we're making that common analogy of comparing voltage to elevation above sea level, well then, a flat ground would be an equal potential surface, okay? So, for example, in the figure, the blue dotted lines represent the 2D cross-section of an equal potential surface. Because when we see something like this, like, a positive charge here, right? And another charge over here, and we think of these as, as maybe like electrons and protons or things like that. And we often draw them as these two-dimensional figures with lots of electric field lines, all following the rules of electric fields. And they're more clustered together. That means stronger field, greater force. And then we have the equal potential lines that by definition run parallel to the electric field. And they get more spread out to represent the decreasing electric field strength and force as a function of distance away from the point charge. Well, when we see all that, it's just a 2D slice, right? This is actually a 3D phenomenon. We always kind of imagine that there has to be field lines in 3 dimensions as well. And if we do, then we know that these dotted lines are in fact equal potential surfaces. Okay, well, let's get to our key formulas related to the physics here. Okay, so then we got some voltage, we got electric field, we've got our line integral. Let's define it all. Okay, so first of all, the idea of the line integral as a picture, just like we saw the idea of the surface integral as a picture, looks like this, right? Here is our curve, all right, going from some initial voltage to some final voltage. And if we want to find the difference along that, then, and we have an electric field that is not constant, maybe the electric field, points the direction shown here, but a moment later, maybe the electric field points this way, and then the electric field points this way, and then back that way, and then over here, and then it's really small, and then, so maybe we have an electric field that's constantly varying. So both the direction and the magnitude of the electric field varies as a function along this line. Well, that means we've got to go and find the strength at every single point, okay? And we also have to do a dot product again, because we care about the component of the electric field that is parallel to the line. It's because here's our line element, here's our electric field vector, the line element itself is the vector. So when we take the dot product, we're just finding the component of the electric field that's parallel to this infinitesimal small section of line called DL, the line element, okay? So same idea, it's a dot product again. So it shows up right here, the difference of the voltages is equal to the negative of the line integral from initial point to a final point of the dot product between the electric field vector and the line element vector, okay? All right, so only the parallel component survives. The negative is because if we're increasing voltage, then the electric field is pointing the other way. If we're decreasing voltage, then we're going down. This is basically just the idea that we're dealing with a force and the direction of the force and the change of potential energy. And as you move in the direction of the potential energy field, you are doing, or there's negative work. You'd be doing negative work to move in that direction. Okay. All right, so V is just the voltage, okay? Here's the line integral of electric field parallel to the path. All right, the line element, as I said, is DL. Good. And then the idea inside the integral, it's a dot product, so we're only looking at the parallel component of the electric field, that's E parallel there, times DL, which is the same as E cosine theta times DL. Okay, very good. Well, what happens as a result of this is the gradient, because that means that the electric field represents the kind of the instantaneous slope of the variation in voltage, okay? Because that's what the electric field is representing here, is the slope, okay? So then we have that the electric field vector is equal to the gradient of the voltage, okay? The gradient of the voltage denoted by this symbol that looks like an upside down delta, okay? Now, in practice, what that is it's the partial derivative of the voltage function with respect to a variable as a component of a vector, all right? So look, we have a partial derivative with respect to x in the x direction, a partial derivative with respect to y in the y direction, and a partial derivative with respect to z in the z direction. And then, of course, x, y, and z are denoted by I hat, j hat, and k hat, as they often are for vectors, okay? All right, we still have the negative relationship here between electric field and changes in voltage. Okay, but that's the idea, is that it's like the instantaneous slope, okay? The electric field is like the instantaneous slope of the surface of the voltage, okay? So the voltage is like elevation, then the electric field is like the slope, and the slope can point in these complicated ways, and the exact direction of the slope, maybe it's pointing a little bit to the east, or a little bit north of east, right? And then at a certain angle down, well, that would be your vector. And we'd find the vector by taking these series of partial derivatives. Okay, so let's see what this is like in practice. Okay, so we have one example that I'm going to do for you. All right, in a certain region of space, we're going to look at electric potential function. Okay, so see, it's a function of 3 variables. Okay, so we know we want to find, if you look here, calculate the x, y, and z components of the electric field at a particular point. Okay, so we're going to find a single vector for the electric field, because the vector for the electric field is changing as you move at different parts of the surface that's represented by the voltage, okay? And also it is noteworthy here that our voltage is just a function of x and y. Notice z doesn't come up. So that means you can really think of it as a surface, right? So if you had x, y, and a z-axis, then what we have here is that the surface would kind of change as a function of, imagine this like a 3D surface, okay? And the idea is there's all these different values at different points on that surface that are, functions of x and y, okay? And then z could kind of represent the output because it's not being used to determine the voltage, okay? But we always still think of it as a three-dimensional vector, okay? So now what we're going to do is we'll just take the partial derivative in each case, okay? So I would look at this whole function and take its derivative with respect to x. Well, then, this term here would just become ay. This term would become 2bx, okay? And then this term here is just a constant, so when I take its derivative, it would just go to 0. So that's everything attached to the I hat vector, okay, according to the way that we do a gradient, okay? Then the same thing for y, all right? And then for z, since there is no function of z, it just goes 0, okay? All right, so there we got our electric field vector. Now that would be the actual form of the electric field vector. We could just leave it like that, in vector form. But now instead, we're going to evaluate it at a particular point in space, okay? And the z is not going to show up because it's independent of z. Okay, so I just simplify it a little bit, and then I plug in my particular values for x and y, all right? Taking note that a and b and c were all defined with appropriate units, okay? These are just constants, all right? And there we have our electric field strength at that particular location for this particular voltage map, okay? All right, good. Now, follow-up question, at which points are components of the electric field equal to 0? Well, let's see. Basically we need to find out where are the 0 points. So I consider setting the x component of the electric field equal to 0 and the y component of the electric field equal to 0. If I do that, then I have these two functions and I can actually kind of set up and solve for them. So I can say that the y component is equal to 0 whenever x is just equal to negative c over a. So there's only one variable here. And then I can then take that value of x and actually plug it back in over here and then find, and that's negative 2.74 meters. And if I plug that value of x back into the expression when x is equal to 0, then I can find a point where both components are equal to 0. See? Because we know that this is a line, right? It is. It's a line. It's any value. This is for any value of y. So any value of y or z, because it's only determining x, right? And so if you look at this is, in other words, it's a line through three-dimensional space where x is held at some constant value, right? And we know exactly what that value is because we know what c and a are, okay? Now, that line then is going to intercept some point where well, that's actually where y is being held at a value of z. But this line is going to intercept a point where the x value is equal to 0. So there's going to be one point where both components of the electric field is equal to 0. One point where there is no gradient, where it's flat in both directions. It would be a two-dimensional equilibrium point. That's what this represents. Not all surfaces would have that, okay? But this surface does, okay? So there we go, and now we're just gonna solve for the value of well, setting this equal to 0, and then we solve for y, okay? And so we go ahead and solve for y, and then we find that the y value that corresponds to 0 is this, okay? So that means that this then forms a coordinate, that single coordinate that is that two-dimensional equilibrium point. And we can find out if it's stable or unstable equilibriums by kind of finding out what the values are to the sides of it. But the point is that here we have a point where there is no electric field. And again, electric field represents the slope of the voltage change. Okay, all right. So hopefully this approach of just taking partial derivatives, kind of evaluating at certain points seems pretty procedural because ultimately it is, but I hope the concepts also make some sense as well. Now, in conclusion, we've defined Gauss's law in its integral form and related it to its closely related ideas of electric field and voltage. Well, I hope this lecture has been interesting and informative. Thank you so much for watching.